This is where we left off. We were talking about steady versus unsteady flows. And so here you can see an unsteady flow versus a long exposure of the same flow. And so the left one is an instantaneous. So it's one snapshot of a picture. And then if you do a long exposure, it looks much more steady. Oscillating wake of a blunt-based airfoil at Mach number 0.6. So photo A is an instantaneous image, while photo B is a long exposure or an average image. And so these are really helpful when, both images are very important, but when you are looking at measuring maybe different things, it's easier depending on if you use a photo like A, which is instantaneous, or a long exposed image like B, time averaged. So 1, 2, and 3 dimensional flows. Just to give you an idea, we will basically look at most in a 2-dimensional performance at basis, and most do. Now, that's not to say that 3-dimensional is not common. It's very common. It's just easier to calculate things, and typically it's sufficient for what we're looking for to just calculate it on a 2D. So a flow field is best characterized by its velocity distribution. Okay, and a flow is said to be 1, 2, or 3-dimensional if the flow velocity varies in 1, 2, or 3 dimensions, respectively. However, the variation of velocity in certain directions can be small relative to the variation in other directions and can be ignored. So this is how we can typically ignore. So we have X, Y, and Z axis, right? And so what we do is we typically ignore Z because typically it's negligible in regard to the maybe profounder orders of magnitude of the velocities in the X and Y direction. So we're just able to ignore typically the 3rd dimension because proportionally it's not significant. So here you can see a developing profile, a velocity profile, which is denoted by V in the direction of R and Z here. So it's in the XY axis. And then you can see a fully developed velocity profile in just the R direction. Okay. And then the development of the velocity profile in a circular pipe, which is velocity RZ, and thus the flow is 2-dimensional in the entrance region and becomes 1-dimensional downstream when the velocity profile is fully developed and remains unchanged in the direction of VR. And so then we're able to look at it once it's fully developed and constant or steady, then we're able to negate the other ones and even look at it on a 1-dimensional aspect. So you can pivot between these 1, 2, or 3. Depending on what you're using, you may go from a 1 to a 2-dimensional, you may go from a 3 to a 2 to a 1. It really just depends on how it's looking and what the devices are and the circumstances of your flow. A flow over a car antenna is approximated by 2 dimensions except near the top and the bottom of the antenna. So uniform versus non-uniform flow. It's pretty self-explanatory. Uniform flow implies that all fluid properties such as velocity, pressure, temperature, etc. do not vary with position. So it's very uniform, right? Doesn't matter what the position is, they're not going to vary. The velocity, pressure, and temperature are going to stay the same. A wind tunnel test section, for example, is designed such that the airflow is as uniform as possible. This is really important. So we know that it's maybe not going to be perfectly uniform, but it's as uniform as possible. And that means that the non-uniform portions are negligible, and therefore we're just ignoring them. Even then, however, the flow does not remain uniform as we approach a wind tunnel wall due to the no-slip condition, right? Because what's the surface? We've got the ground, we've got the ceiling, we've got the walls. We're going to have a no-slip condition in the presence of the boundary layer. The flow just downstream of a well-rounded pipe entrance is nearly uniform, again except for a very thin boundary layer near the wall. In engineering practice, it is common to approximate the flow in ducts and pipes, and at inlets and outlets as uniform, even when it's not, for the simplicity of calculations. This is because at some point, you have to stop measuring to calculate, right? So if we are to look at things on a macroscopic level, we have to make certain assumptions. We have to make certain things constant, certain things steady, so that we can start the calculations. You obviously don't want to do it too early because then you're not getting enough usable data. But when you're trying to include things that are negligible or things that are not actually going to impact your end result or your end conclusion, then you're just wasting time. And there's no end to what you could calculate. You can always calculate it on a smaller level. You can always be in search of devices that are able to calculate more accurately. If we were to calculate every portion of the changes or the connectedness or the force of the molecular bonds, we would spend so much time calculating that we would never calculate any usable data. So therefore, with enough testing and enough experimentation, we've gotten a lot of data and formulas that for you and for me and for the industry let you know the starting point and stopping point, where it says, we're just going to negate this. We're not going to pay attention to this, things like that. So let's talk about the system and the control volumes when we are doing our calculations. The system is the quantity or matter of the region of space chosen for study. The system is what you are concerned about. Okay? If you are a doctor and you're a heart doctor, you're concerned about the heart. You're not concerned about fingernails. You're not concerned about eyes. You're not concerned about all these other things. Your system is the heart. The system is what you are looking at. And outside of that, the mass or region outside the system, that means that everything outside of the heart, everything outside of the system that you're looking at, that's the surroundings. Sure, it impacts. Sure, it's relevant, but it's not what you're concerned about. You are concerned about the system. If you're a heart doctor, you are concerned about the heart. Everything else out of that is secondary, right? The boundary is the real or imaginary surface that separates the systems from its surrounding, okay? The boundary is the walls. It may be real, it may be imaginary, right? So if you're a heart doctor, you can say, well, the walls of the heart is my boundary. Or you can say, well, this imaginary area, including the valves, and the heart, and everything, the inlets and outlets off of the heart is now my system, and here's my boundary. Here, I'm going to draw it in my mind, right? And with that, the boundary of a system can be fixed or movable, right? So you can move the boundary if you need to. You can make it bigger or smaller if you need to, or it can be very fixed, like a house, right? Everything inside the house is a system. Everything outside of the house is the surrounding, and the walls is the boundary. A system may be considered closed or open. And what does that mean? Well, that means if a system is closed, that means that there's no mass interaction between the system and the surroundings. We're not talking about heat. We're not talking about energy transfer. If you've taken thermo, this is a big portion of it. If you haven't, it's a foundational concept. This is, but when we're talking about something being closed, that means there's no mass interaction. Okay, the fluids that we're concerned about, they all have mass. Okay, there's a mass of a gas, there's a mass of a liquid. Doesn't matter what it is, it all has mass. Okay. And if a system is closed, you are not going to have any mass come in from the surroundings to your system, and you're not going to have any mass exit your system exit to the surroundings from your system. Or your system can be open, which means there can be a free flow whether it be from one designated point or because your boundary is imaginary. There's a free flow of mass in and out of your system. Closed system, this is actually the result of the example of a piston. A closed system or a controlled mass, because there's no mass change, so we're controlling the mass in a closed system. A fixed amount of mass and no mass can cross its boundaries. So you see here, the gas itself is still 2 kilograms between state 1 and state 2. When we're talking about states, we mean like the first instantaneous snapshot that we take is state 1. And then state 2 is after a certain amount of time, we take another instantaneous snapshot, right? So this moving boundary, we took a picture when this boundary was right here, and then an amount of time passed here, it moved up, and then we took another picture where this boundary was there. That's a moving boundary. Okay, this is a closed system. Our gas is still 2 kilograms, never moved. We did apply some heat here, which made our gas expand and cover more area. So we're covering more area, but we didn't add any gas, okay? Open system or a control volume, right? So this one is control mass, so no mass is changing. But an open system is a control volume, so what are we able to do there? We're able to control the volume of it, right? Because we have boundaries. So a properly selected region in space. It usually encloses a device. It usually encloses a device that involves mass flow, such as a compressor, turbine, or nozzle, something that it can flow. Both mass and energy can cross the boundary of a control volume. A control surface is the boundaries of a control volume. It can be real or imaginary. And here's them denoted. It's basically the same as before. But you see this over here on the right, this piston here, we now have an inlet, right? So mass can come in, right? Okay. And then here we have a nozzle, which is a device, and we have a real boundary right here, real boundary because it's the nozzle, but then we have an imaginary boundary, right? And so now we have what the volume in which we are looking at, right? So we are looking at the volume, our system within this imaginary boundary. We are controlling the volume, but our volume's staying the same, but the actual molecules within our volume is definitely changing, right? So if we have, let's just say for easy math, this is 2 gallons, this is water flowing through a nozzle, and we're able to have 2 gallons in this very large nozzle, right? So say we have a molecule over here, and we have this force going this way. So we have this force, and it's going, and that molecule is changing, right? It's going through, it's going in, and now it's exiting the nozzle, and it's flowing on through. But we still only ever had 2 gallons. We still controlled the volume. We only ever had 2 gallons. You can change that. Here, if you have fluid going in here, I can push and go to a certain point, and we will have control volume, and it will move up. But what if we have stops here, right? And then it's able to come here, right? It'll stop, and that'll be the end of it, or it can keep going. Either way it goes, we are able to control the volume. It's not just the atmosphere where we're not controlling the gas that's being expelled into it, right? So here's the importance of dimensions and units. I do want to make this extremely clear. The dimensions and units are detrimental to at least a handful of students every semester. And that's because you have to calculate on homogeneous units. You have to use the same units. You cannot calculate something in feet and also in meters. Okay, you can if you convert the meters to feet, or if you convert the feet to meters, but you cannot multiply 4 feet times 12 meters and get some sort of usable information. There's not a unit that says feet meters. It is imperative that you do your diligence, your due diligence, and double check. It should be the first thing that you're looking at, is to making sure that you're using homogeneous or the same units. It's extremely important, okay? So any physical quantity can be characterized by dimensions. So any type of dimension, and then the magnitudes assigned to the dimensions are called units. So we've got basic dimensions, right? Mass, M, L for length, T for time, and then capital T for temperature. And we select those as primary or fundamental dimensions, while velocity, V energy, E, and V volume are expressed in terms of primary dimensions and are called secondary or derived dimensions. And that's because we calculate those from our primary, right? So 2 types of unit dimensions that we use is the SI system. It's a simple and logical system that is based on a decimal relationship between various units. And then English system, or EE, has no apparent systematic numerical base, and various units in the system are related to each other rather than arbitrary. So it doesn't start somewhere, but it has a strong relationship with each other. But the SI system is built upon a base versus a relationship. So here is just a table. It's very easy. So we've got what you would use for length, and that's meter, mass, things like that. And then over here on the right side, you have a standard prefix. So you have kilo, hecto, deci, milli, things like that. And this is all for SI. Okay. And then here's some standard SI and English units. So 1 pound meter converted, right? Because pound is not kilo, right? So 1 pound meter is equal to 0.45359 kilograms. 1 foot equals 0.3048 meters. Work equals force time distance, and you have that in joules, BTUs, kilojoules. You have more force times mass. Force equals mass times acceleration, and you've got that over in kilograms times meter over second squared, and then you also have it in pound force as well. So in newtons of force, you have it in the SI unit prefixes are used in all branches of engineering. You are going to get very good at this, and you can convert. Just make sure that you are using homogeneous units. Make sure you're not trying to use SI and EE before you convert. And I promise everyone in this class is going to do it. I'm not asking you to not do it. I'm asking you to catch it, because it's going to mess up your calculations and you will not get a right answer because it's not right. So here, this is the relative magnitude. So when you're talking about maybe orders of magnitudes of force units, Newton, kiloforce, or kilogram force, and pound force. And so here you can see weight equals mass times gravitational acceleration. A body weighing 150 kilogram force on Earth will weigh only 25 pound force on the moon. So something that I want everyone to remember is that we are doing all of these calculations and everything on Earth, unless otherwise noted, right? So we are going to have things like atmospheric forces. We're going to have gravitational accelerations. We're going to have things like that. And we are assuming that all of that is given for Earth data, right? We're not calculating things on the moon, okay? And so here you can just see that you have 1 kilogram force going above on top of the head. 10 apples equals 1 kilogram. And then you have, 1 Newton over here, and then you have 1 pound force. So it's just showing you the difference in 1 kilogram versus 1 Newton versus 1 pound force. And then the weight of a unit mass at sea level. So not only are we looking at it on Earth, but we are also looking at things from an elevation standpoint as well, because that also yields different results, right? So typical match yields about 1 BTU or 1 kilojoule of energy if burned completely. And then here, something that's very important to note, these are our gravitational constants. So our gravitational constant, 9.807 meters per second squared, or 32.174 feet per second squared. And these are your gravitational constants that you will need to have. So we talked about this. All equations must be dimensional homogeneous. I cannot take answers in non-homogeneous units because it's not math. It's not correct math. That would be like writing a paper in both, Greek and English. It's like I can only read half of it. Doesn't make sense. All non-primary units, secondary units, can be formed by combining the primary units. So it's just like colors. If you have primary colors, you get secondary colors from primary colors. If you have primary units, you get secondary units from primary units. And here's some unity conversion ratios. So this is just conversions, right? So a Newton over kilogram times meter per second squared is equal to 1, things like that. So unity conversion ratios are equal to 1 in our unit lists, and thus such ratios or their inverses can be inserted conveniently into any calculation to properly convert units. This is just so that you can convert the units. Okay, again, it's really big. Even the PowerPoint's telling you. Every term in an equation must have these same units. It should be the very first thing you do. When you start getting data, because you're going to use like given information as well and stuff like that, you need to be converting. You need to be getting your terms to homogeneous units. Okay, and here's some easy ones, and we'll go over some, but 1 minute is equal to 60 seconds. You know what, let's just do one of these really quick, just so that you can see it. So if I have 120 seconds and I need it to minutes, of course you could do that in your head, but I'm just wanting to make it very easy for you to use the conversion. So if we have 120 seconds and I need that to minutes, let's do 120 seconds. That's my unit. I know I can put that over 1 because I can put anything over 1, right? And then I'm going to multiply it by my conversion. Multiply it by 1 minute over 60 seconds, okay? So here, I'm going to just multiply across, right? And I'm going to cancel out my units, right? So then I have 120 minute over 60, and then that's going to give me 2 minutes, right? Okay, and so what you're doing is you're canceling out the units by converting. 1 pound, a mass of 1 pound weighs 1 pound force on Earth. So we're looking at Earth, right? Okay, so modeling and engineering, an engineering device or process that can be studied either experimentally, just testing or taking measurements, or analytically by analysis or calculations. Okay, so either one of those is an engineering device or process, and it's the way that we can study them. An experimental approach has the advantage that we deal with the actual physical system, and the desired quantity is determined by measurement within the limits of experimental error. However, this approach is very expensive, time-consuming, and often impractical. So what this is saying is if you look at it as an experimental approach, okay, if you are going to design a car and you are going to take the experimental approach, that means you have to build the car. You have to build the physical system that you're looking at, because your system is what? The car, right? And you need the physical car. So you're going to do that. And then you're going to do all of your experimenting. You're going to do all of your measurements. You're going to do all of that. And then guess what? Is your first car going to be the correct one? Absolutely not. So you're going to have to build it again and again and again and again and again and many, 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 many times. And it's going to be expensive and time consuming and extremely impractical. This is not used. Actually, this is used as a last resort situation, right? But an analytical approach, which is the numerical approach, has the advantage in that it's fast, inexpensive, but the results obtained are subject to accuracy and assumptions, approximation, and that idealized in the analysis. This is when we're using things like CAD, right? When we're modeling something in a system, and we do it over and over and over and over and over again to get it as far as we can in the analytical approach before we move to the experimental approach, so that there's less experimental time. The analytical approach is to become fast and cheap and accurate, right? It's as accurate as the assumptions that we can make, because we have to make assumptions when we're calculating. We have to make approximations, right? So when we say that this length is 3 meters in a analytical approach in CAD, AutoCAD or SolidWorks or another modeling software, well, then it's going to be exactly 3 meters. But when we go to build it, is it going to be exactly 3 meters? No, it's going to be approximately 3 meters, right? So we have approximations, assumptions, idealizations. We'll get into that a little later, but we use the analytical approach to look at anything, testing, measurements, study anything, and take it as far as we can before we get into the experimental approach to reduce the amount of experimental approach that we need. So let's talk about why we need differential equations. I know that you guys have started using differential equations, and we're going to use them here, and you also use them in thermo as well. So the descriptions of most scientific problems involve equations that relate to changes in some key variables to others, right? So in the limiting case of infinitesimal or differential changes in variables, we obtain differential equations that provide precise and mathematical formulas for physical principles and laws by representing the rates of change, which is derivatives. So what we're doing is when we get really, really, really long equations, and these equations represent multiple parts or multiple devices within a system, maybe one of these flows is what we need to change, not everything. And so the way that we can do that is by using differentials or derivatives. Differential equations are used to investigate a wide variety of problems in sciences and engineering, so we use them a lot. Do we always need differential equations? Many problems we encounter in practice can be solved without resorting to differential equations and the complications associated with them, but we will be using them. So here is a physical problem. We identify important variables, apply relevant laws, make reasonable assumptions, but then we do need to get into differential equations where we apply applicable solution techniques, apply boundary and initial conditions, right? So when we have an entire equation, but we have changing conditions within that, right? Like a flow of something, then we would use a differential equation. And then that's how we can get to the solution of the problem. A complex model, which is very accurate, versus a simple model, which is obviously not so accurate. Here you can see an actual engineering problem versus the minimally essential model of an engineering problem. And so this is just saying that we use simplified models. And that's where we can get like quick and dirty answers, approximate solutions to difficult engineering problems. And so this is something that if we have an engineering problem and we want to say, well, does this even work? worth it, then that's when you make a lot of assumptions. You negate a lot of things, and you're like, hey, this actually produced an answer we can use. And that's when you can go a little bit further and go a little bit more in depth and a little bit more in depth. So here's a problem-solving technique, and we'll go over this, but I do recommend it. It's where you write your problem statement. It's where you draw a schematic. Schematics are incredibly important. This is a very visual topic, and so drawing schematics really help to connect what you're doing with what you need to find. You have assumptions and approximations. You always need to write your assumptions and approximations, because you may be equating some things to zero or neglecting some things, and you need to state that. You need to state some of your assumptions and some of the approximations. You need to take into account your physical laws and, of course, the properties of the fluids that you're going to be looking at. And then you're going to be doing your calculations, which should also have your homogeneous units. And then down here, it's the reasoning, verification, and discussion. That's step 7. It's a little, unless I ask you, your answer is sufficient, right? So unless I say, can you put some reasoning behind it? Can you verify it? How can you verify it? Can you discuss your answer and tell me why? Unless I do that, your calculation is going to end here. Something that I do want to do with the calculation is your final answer. Any work that you turn into me, right? Or like your background calculations, things like that. Your final answer needs to be blocked in, and you will receive a few points off if you don't, even if you have the right answer, because these formulas and these equations that you're going to be solving are extremely large. Some of them are pages. You need to have your final answer blocked, because you're going to have a lot of answers within one problem, and you need to get to your final answer. So here is a step-by-step solution. You can try and do it the hard way, and you can try and just kind of do it all at once and not state your assumptions and maybe not find the not blocking your final answer. And that's the hard way. I mean, you may get there, but chances are you won't. But your easy way, and this is something that I implored when I was in college, and it's something that I've kept, it's definitely a lot easier, right? And so in here you have stuff that you're given. You know what you need to find, because how can you start on a path if you don't know where you're going? And your to be found, what the question's asking for, will give you that where you're going. Missing pressure, you're identifying what you need, right? Oh, okay, I need to find that. And then you can talk about your assumptions, things like that, right? And so here, this is before streamlining and unreasonable after streamlining, which is unreasonable. It's just neatness and organized are highly valued by employers. I do say, coming out on the other side of it and now being an educator, and then also working in the private sector as well, that for me, my undergrad work was the time that I really solidified being neat and organized, and it was out of necessity to succeed in the courses. So definitely lean into that and really take the time now to develop those skills. It will pay dividends long after you graduate. So all this says is there's a lot of packages out there. Obviously, you're not doing all of these hand calculations all the time in the real world, but you do need to know how they work, because otherwise, unlike a calculator where you can just sometimes type something in, or like a solver online, you in the real world need to know how the formulas work, because you need to be able to have worked them so that you can go and get the data. So they're not as sophisticated as some of the other tools or solvers that we use in everyday life, but they do exist. And here's some of them. EES is a big one, and of course Excel. CFD, computational fluid dynamics. So it just talks about different CFD software, and it's where you can model actual flow of fluids. So it's computational fluid dynamics, so the flow of fluid in a computer software. Accuracy, preciseness, and significant digits. So the accuracy error, inaccuracy is a value of one reading minus the true value. And then precision error is the value of one reading minus the average of readings. And then significant digits is the digits that are relevant and meaningful. Okay, and so this just talks about shooter A is more precise but less accurate, while shooter B is more accurate but less precise. And then this goes into sig figs. So you will be asked to either give the number of digits after or the significant figures associated. And so here, the easiest one to count is that these are all three sig figs. Okay, and then exact time span. An instrument with many digits of resolution, a stopwatch, may be less accurate than an instrument with few digits of resolution, stopwatch A. So really just to go over the summary, we introduced a lot of concepts. We talked about that no-slip condition where there's a lot of friction involved, and we're creating that boundary layer. Brief history of fluid mechanics is very old. Classification of fluid flows, and we talked about laminate, turbulent, transient, things like this. System and control volumes, and that's when we started talking about masses being able to move in and out, closed systems, open systems, things like that. The importance of dimensions and units, extremely important. We want homogeneous units, right? Modeling and engineering, we talked a little bit about that and about what we can do and about CFD analysis. Problem-solving techniques and just recommendations, especially proven recommendations for students on how to solve the problems. Take them. They are recommended for a reason. They're not recommended to just give you more time, right? It's recommended because it is proven. Engineering software packages, there's a lot, but we're going to be learning how to work them. And then accuracy, precision, and significant figures. We're going to watch a short video that was produced that kind of gives a brief overview of Chapter 1, but just some other schematics, and hoping it's helpful.
Welcome to the ancient and modern field of fluid mechanics. Fluid flows, gases or liquids, are all around us, from the very small to the very large, from the very slow to the very fast. Fluid mechanics is important in everything from sports and recreation to transportation to national defense. There are fluid flows inside our bodies as well as other fluid flows outside. We're going to start by introducing a wide variety of fluid flows, both experimental and computational, and discussing how these flows are classified. First, we classify flow regions as viscous or inviscid. Consider the viscous and inviscid regions in the flow over an airplane wing. This computational fluid dynamics, or CFD, animation shows colored contours of airspeed over a wing with an oscillating flap. Very close to the wing's surface is a thin layer known as the boundary layer. In it, viscous forces are important and cannot be ignored. However, outside the boundary layer, viscous forces are negligible compared to the inertia of the flow. We call this the outer, inviscid flow region. This distinction, due to Ludwig Prandtl, was one of the key developments in 20th century fluid mechanics. We also classify flows as internal or external. An internal flow is surrounded by walls, as in this computation of a train passing through a tunnel. Once the train is outside the tunnel, the airflow around the train is now an external flow. Likewise, flow over an airplane is external flow, while flow through a jet engine that powers an airplane is internal flow. Next, we classify flows as incompressible or compressible. Most liquid flows are incompressible. Thus, we keep the fluid density constant when we solve the equations of motion. Gas flows are also incompressible at speeds much less than the speed of sound, as in the airflow around a toy airplane or around a spinning football. However, high-speed gas flows are very compressible. Here's a high-speed movie of firing a rifle bullet and a simulation of a bullet emerging from the muzzle of a gun. Shock waves and other fluid phenomena happen here that cannot happen at low speeds. Another way to classify flows is laminar versus turbulent. Laminar flows, like the beginning of this plume from a candle flame, have smooth, ordered layers of flow with only molecular mixing between them. Turbulent flow occurs when the inertial forces dominate the viscous forces, which eventually happens at a higher location in the candle plume. Turbulence has unsteady swirling vortices or eddies of various scales. These eddies cause strong mixing in turbulent flows, which are clearly much more complicated than laminar flows. Still another way to classify flows is natural versus forced. Natural flows do not involve fans, blowers, or pumps to move the fluid. Instead, it flows by itself as a result of some natural effect, such as buoyancy. Natural convection is sometimes sufficient to cool electronics, for example. Forced flows, on the other hand, are driven by some external means, such as the built-in fan in this laptop computer, or the water pump driving this pipe flow. Another classification of fluid flows is steady versus unsteady. By carefully adjusting the kitchen faucet, we can produce a stream of water that is not only laminar, but also steady, except for an occasional wiggle. The stream of water from this garden hose is turbulent, as one can tell from both its appearance and its sound. However, the water pressure that drives it, the nozzle diameter, and the speed of the stream are all constant on average if one ignores the turbulent fluctuations. We call this a stationary flow, or a flow that is steady in the mean. However, some flows, such as the gas flow inside an internal combustion engine, are inherently unsteady. The flow pattern is always changing with time. Even the boundary conditions are changing. As the piston cycles inside the cylinder, the volume available for gas motion, shown in this CFD simulation, varies periodically. In some applications, like this wing undergoing a slow pitching motion, we can approximate the flow as steady at any given instant, even though the flow field is really unsteady in principle. Such a flow is said to be quasi-steady. Our final classification is 1-, 2-, and 3-dimensional flows. Reality has 3 space dimensions. However, it's very useful in fluid mechanics to concentrate on fewer than these 3 dimensions for simplicity. For example, the flow through a pipe has 3 space dimensions x, y, and z. But often we're mainly interested in what changes along the pipe. Many pipes are so long compared to their diameter that we can neglect the change of parameters across the flow and consider only what changes with length of the pipe in the x direction. This is a one-dimensional flow approximation. Here is supersonic airflow through a converging, diverging Laval nozzle. One-dimensional inviscid theory in the x direction is sufficient to describe this flow, except for the viscous boundary layer at the walls. Here, these are quite thin and can be ignored. However, the flow over this wedge requires a two-dimensional theory in x and y. When the normal shock wave moves back up the nozzle, its interaction with the boundary layers becomes too complicated for any simple theoretical model. In the aerodynamics of birds and airplanes, We can often examine the flow in X and Y over the cross-section of a wing and ignore any changes in the direction of the wing span, Z. Here is such an example in a wind tunnel where smoke is used to visualize the flow. The length of the airfoil in the flow direction is called its chord length. The airflow over a glider wing is approximately two-dimensional as well, since the wing span is much larger than its chord. Such a wing is said to have a large aspect ratio. In this case, the wingtip and root are so far from a section at mid-span that they may as well be infinitely far away. A similar argument can be made for the wings of this waved albatross, more than 3 meters in span. The flow in a soap film is also very two-dimensional. The film's lateral dimensions are several centimeters, but the thickness is only a few micrometers, seen in color due to white light interference phenomena. On a global scale, the Earth's weather can be considered two-dimensional as well. In this NASA footage of Hurricane Isabel, the view spans thousands of kilometers, but the atmosphere itself is only about 100 kilometers thick. Thus, such large weather phenomena cannot go over the top of one another. They must go around. Often the gross features of a 3D flow can be observed by modeling the problem in only 2 dimensions. Here a buoyant, top-heavy block falls into a pool of water. A 2D CFD simulation reveals many features of this flow. The full 3D unsteady simulation shows some additional phenomena, but it takes at least 100 times longer to compute. In order to produce a fully three-dimensional flow, we fed theatrical fog into the bottom of this can. It makes a messy, turbulent 3D plume. A modern way to study such a complicated flow is to illuminate it by a thin sheet of laser light, thus slicing the 3D flow into two-dimensional sections. Many flows of practical interest are very three-dimensional. That's the case for the envelope of shock waves that surrounds this model of the Space Shuttle orbiter, here being tested at Mach 3 in a supersonic wind tunnel and imaged using a color Schlieren technique. Despite the complicated nature of this flow, we can still use approximate methods of fewer dimensions locally, such as a 2D flow approximation at the wing leading edge, to help understand the basic fluid dynamic building blocks that combine to make up real, practical flow fields.